Here is another example of a recurrence for which we shall discover shortly that master method does not apply. T of n is 4 times T of n by 2 plus n square times log n. The value of the coefficient a is 4, the value of the coefficient b is 2, and the function f of n is n square log n. So let's compute n to the power log base b of a. That turns out to be n to the power log base 2 of 4. And log base 2 of 4 is 2. So n to the power log base 2 of 4 is n square. So how does n square compare with n square log n? Well, it's clear from a simple comparison between these two functions that f of n has a larger rate of growth, right? And uh, we don't even need to take the ratio. We already know that f of n has this log n factor extra. So f of n has a larger rate of growth than n to the power log base b of a. And taking the ratio just confirms that. If you take the ratio, you'll get log n, and as n tends to infinity, this ratio is going to tend to infinity. So f of n has a decidedly larger rate of growth than n to the power log base b of a. One can say that f of n is in big omega of n to the power log base b of a. More strongly, one can even say that f of n is in little omega of n to the power log base b of a. But the question is f of n polynomially larger than n to the power log base b of a? We know that it's larger, but is it polynomially larger? It needs to be polynomially larger in order for us to apply case 3 of master theorem. Case 1 and case 2 are ruled out because case 1 is when f of n is polynomially smaller than n to the power log base b of a. And since f of n is in big omega of n to the power log base b of a, it cannot be polynomially smaller than this function. Similarly, case 2 doesn't apply because the two functions don't have the same rate of growth. F of n has a larger rate of growth. It has an extra log n term. So the rates of growth of these two functions are different. And so case 2 doesn't apply. For case 3 to apply, we need to first verify that f of n is polynomially larger than n to the power log base b of a. That's why we are asking this question. Another way to ask this question is, can we add a small power, say epsilon, some constant epsilon, to log base b of a and still have f of n in big omega of n to the power log base b of a plus this epsilon. So can we prove that f of n is still larger than this resulting function with n to the power epsilon added on to what it was before? Because if f of n is polynomially larger than this function, it should be possible for us to slightly increase the power of n here and still have the resulting function grow slower than f of n, or have f of n grow faster than this function. So let's check what the ratio of the two functions is after adding this plus epsilon. So f of n is n square log n and log base b of a is 2. So this ratio will become n square log n divided by n to the power 2 plus epsilon. N square and n square cancel and we are left with log n in the numerator and n to the power epsilon in the denominator. Now this is an infinity by infinity indeterminate form in the limit because both the numerator and denominator tend to infinity as n tends to infinity. So we can independently differentiate both the functions. We'll get 1 by n in the numerator and epsilon times n to the power epsilon minus 1 in the denominator. Now this power of n, this n will come down into the denominator and it will add 1 to the power of n here. So the power of n will become epsilon minus 1 plus 1, which is going to be epsilon. And this fraction tends to 0 as n tends to infinity because we have an infinity term in the denominator. N to the power epsilon tends to infinity as n tends to infinity. So this limit will be 0. This means that the ratio of these two functions is 0. So f of n is definitely smaller. It has a smaller rate of growth than this function. And this fact is independent of what the specific value of epsilon was. As long as it was a constant that was positive, the ratio between these two functions is going to be 0. So even though the ratio of f of n and n to the power log base b of a without this epsilon was infinity, just by adding a small power to the existing power of n here, the ratio comes down to 0. So the relationship between the functions is reversed. Without the epsilon, this function was larger than this function. With the epsilon, this function is larger than this function. Since f of n is smaller than n to the power log base b plus epsilon, f of n cannot be in big omega of this function. Doesn't matter what the exact value of epsilon was, as long as it was some positive value. So f of n is not polynomially larger than n to the power log base b of a, even though it is larger than n to the power log base b of a. F of n has a larger rate of growth than this function, but it's not polynomially larger. This means that we cannot apply case 3 of master theorem. And we've already seen that case 1 and case 2 don't apply. So we cannot apply any of the 3 cases. This means we can't apply master theorem here. F of n falls into this gap on the other side of n to the power log base b of a. In the previous example, we saw that the f of n there fell into the gap to the left of this point. In this example, the function we picked falls into the gap to the right of this point. So the function that we have, n square log n, is to the right of n to the power log base b of a because it has a larger rate of growth than this function. But it's not polynomially larger. This means that if you actually take any polynomially larger function than this function, any function that's polynomially larger than this, that function is going to fall in this green region, which is to the right of f of n. So these functions grow larger than f of n and they also grow larger. They grow polynomially larger than n to the power log base b of a. F of n is larger than n to the power log base b of a, but it's smaller than any function of the form n to the power log base b of a plus epsilon, or any function that has a larger rate of growth than a function that is polynomially larger than n to the power log base b of a. So even though we cannot apply master theorem to exactly solve for t of n, as in the previous example, we could use master theorem to narrow down the range in searching for the exact asymptotic complexity of t of n. For example, we could increase this function n square log n to n to the power, say, 2.01, or in general n to the power 2 plus epsilon for some small value of epsilon. Now the resulting function n to the power 2 plus epsilon would be larger than f of n. Why? Because if we take the ratio of this function to this function, that ratio would be n to the power epsilon divided by log n, because n square would cancel out. And we have seen in this very video that the ratio of log n and n to the power epsilon is 0 in the limit. Doesn't matter what epsilon is as long as it's greater than 0. Putting it another way, the ratio of n to the power epsilon divided by log n is infinity in the limit. So when we take the ratio of this function to this function, we get n to the power epsilon divided by log n, and that ratio is infinity in the limit. So by substituting n to the power 2 plus epsilon in place of this function, we are increasing the value of the function that represents the amount of work needed to combine the solutions to the subproblems. Now we can work with this larger function and look at this recurrence. I'm using t sub u here to denote that what we are going to get by solving this recurrence is an upper bound on the original t of n. And this recurrence can be solved directly using master theorem. A is 4, b is 2, and n to the power log base b of a is n square. F of n is n to the power 2 plus epsilon for some positive value of epsilon. So f of n is polynomially larger than n to the power log base b of a. And we don't need to check the regularity condition here because f of n has exactly the form n to the power log base b of a plus epsilon. So we can use case 3 of master theorem and claim that t of n is theta of f of n, which is n to the power 2 plus epsilon. So if we had chosen this specific function n to the power 2.01, then t of n would have been theta of n to the power 2.01. So this is an upper limit on t of n. We could remove this log n factor and just work with n square and thereby get a lower bound on t of n. Right, so we could have changed f of n to just be n square instead of n square log n, and this would be the resulting recurrence. T of n would be 4 times t of n by 2 plus n square, and I'm using t sub l of n to represent the fact that the solution to this recurrence is going to be a lower bound on the original t of n. So if we try to solve this using master theorem, we'll again get a is 4, b is 2, and n to the power log base b of a is n square. But our f of n here is also n square. So both functions have the same rate of growth. This means that case 2 of master theorem can be applied, which tells us that the solution to this recurrence is theta of n square log n. So we have an upper bound on T of n and we have a lower bound on T of n. So we can say that the actual asymptotic rate of growth of T of n will lie somewhere between these bounds. The upper bound is n to the power 2 plus epsilon. The lower bound is n square log n. It turns out that the actual rate of growth of T of n is n square times the square of log n. So note that this function is larger than this function. It's larger than this lower bound, but it's still smaller than the upper bound. Now it may not be obvious that this function is smaller than the upper bound. So let's try to take the ratio of the two functions and see if the ratio really tends to 0 as n tends to infinity, putting this in the numerator and this in the denominator. N square log n square divided by n to the power 2 plus epsilon for some constant positive epsilon. So n square will cancel in both the numerator and denominator, and we'll get log n square in the numerator and n to the power epsilon in the denominator, with limit n tending to infinity, of course. Again, we get an infinity by infinity indeterminate form, so we can use L'Hopital's rule and differentiate the numerator and denominator independently, in which case we'll get limit n tending to infinity twice of log n multiplied by 1 by n. That's the derivative of the numerator, and epsilon times n to the power epsilon minus 1, which is the derivative of the denominator. Now this 1 by n, this n in 1 by n will get added to, will get incorporated into the denominator and will add 1 to the power here. So this is going to become twice of log n divided by epsilon times n to the power epsilon, of course as limit n tends to infinity. Now we already know that log of n divided by n to the power epsilon as n tends to infinity is 0. We just calculated that over here. So we know that this function therefore has a smaller rate of growth than this function. So this function is an upper bound on this, and we already have a lower bound. So even though master theorem couldn't exactly solve this recurrence, we could still come close by sandwiching the actual complexity between an upper bound and a lower bound. It turns out that there is an extended version of master theorem which does handle cases of this type. Where f of n is not polynomially larger than n square, but we can say that its f of n is theta of n times n to the power log base b of a multiplied by log n. Right? N to the power log base b of a is n square. So f of n is theta of, it's not exactly theta of n log n to the power log base b of a, but it's theta of n to the power log base b of a multiplied by a logarithmic factor. There is an extended version of the master theorem that we have seen which handles cases of this type. We will look at that in a future video. We will look at that extended version in a future video and see that we can still work with this recurrence and that extended version of master theorem and directly get a solution to the recurrence, which is given by this function. T of n is n square times log of n square. But here I just wanted to show you that there is a function like n square log n, which with respect to n square is larger than n square, but is not polynomially larger. And if you work with the version of master theorem that we have seen so far, we can't use the theorem to solve exactly for the recurrence. Even though we can come up with an upper bound and a lower bound on the actual asymptotic complexity, we can't exactly solve it.